So, good evening, everyone. I welcome you all to this fourth-day session on inferential statistics. As we have learned in last 3 days that statistics helps us to overcome the bias of human brain and therefore provides a much better ability of decision making with given scientific data. So today's session is mostly about making decisions on your hypothesis. So, so let us get back uh, to the same idea of scientific method described to uh, described to you in previous data of this workshop with a more emphasis on hypothesis. So in more textbook terms, a hypothesis is defined as supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation, which means your own thought or personal solution about a problem. So let us understand this with the help of a simple day-to-day life example. So suppose you came to your house in the night and then switched on the bulb, but unfortunately it didn't glow. This represents a problem. Now, what will you start thinking? Maybe there is uh, no power, or maybe bulb has gone bad. So you have two hypotheses in your mind, and there may be even more. So what you will do next? You would check the light in adjacent buildings. If there is no power anywhere, your first hypothesis was true that there is no power. And but everywhere else power is fine. And so what you will think? Uh, your second hypothesis is right. Same is true in scientific work. You develop hypotheses and then test them and then choose the correct one. All right. So in fact, there are two commonly used terms in scientific world, namely null hypothesis and alternative hypothesis. So if we keep it simple, then if what we think is not true, that is called null hypothesis. But what we think is true is it's a alternative hypothesis. All right. So the null hypothesis is symbolized by H naught, while the alternative hypothesis is symbolized by H1 or HA. Okay. So, all right. In more simple words, something that you expect in alternate hypothesis and something that you don't expect in null hypothesis. So a very famous cartoon from one of the book on statistics make it relatively simple to remember the two terms. Okay, all right. So let's now learn how to test the hypothesis. So we take one example here that we have a plant extract and we expect that it can cure diabetes. So our expectation is our alternate hypothesis, and against our expectation is the null hypothesis. But the question is how we will test the hypothesis. How we will test this hypothesis. So that is by experimentation. So we look, we took two group of diabetes rat, and one group was not given drug called control or placebo, and the other group was given some drug named test group. And let's say we had some 10 animals in each group, in control and in the treated group. And then what we will do, we will monitor the glucose level. Now, okay, so now if the result appeared like this, 8 out of 10 animal were cured, and their glucose level was in the normal range. So should we start saying that or believing that our drug is wonderful? Not essentially. Think about a situation that it would have happened by random chance. What if some of the rats, what if the sum of rat in control or placebo group also got cured for diabetes by themselves? I mean, got cured for diabetes by themselves. So uh, here we need help from statistics, as our mind is very good at making patterns, and thus it can quickly create bias that drug is effective. But without performing inferential statistics, it is difficult to comment upon the exact phenomena. So we have a parameter called p-value that predicts if results were obtained by random chance or by actual effect of the drug, and help us to select the right hypothesis. The statistical parameter is called p-value. It is the probability of getting the result by random chance. All right. So let's uh, l- l- look into this in a more details using our some diabetes example. So in case 1, when p-value is higher, say 0.56, indicates that there are 56% chance of diabetes being cured by random chance. So in that situation, we would reject the alternative hypothesis and accept null hypothesis. Alright. However, if the p-value is very low, that is 0.01, so in that case, the random chance of curing diabetes is very low. That is just 1%. That is just 1%. Okay. So it must have been cured by the drug. Hence, we accept alternative hypothesis. Got it? So, uh, in general, a p-value of less than 0.05%, that is 5%, 0.05, that is 5%, is considered significant. But for clinical experiments, uh, it is expected to be less than 0.01. However, there is a lot of debate on the use of this value in scientific community. Okay, so now let's see how and when we may commit error while inferring the result. There are two types of error known. Type 1 error, that is false positive, and type 2 error, that is false negative. Type 1 error is one where you reject the null hypothesis by mistake, whereas type 2 error is one where you reject alternative hypothesis by mistake, or you accept null hypothesis by mistake. That is, in case of type 1 error, you infer that it does not work, but it was actually working. While in case of type 2 error, you propose that the drug works, but it actually doesn't. Hope that helps you understand the hypothesis testing and types of error. Now let's try to understand we might commit those errors. So here is a probability distribution of glucose level. As you can see, it's a normal distribution graph where you can expect both type of animals, some with a higher glucose level even after the drug, and some animal with low glucose level, and most with a median glucose level of 7.5 mm. So in the first case, if your animal or experimental group did not represent complete population, but animals belong to some of the extremes, uh, so if your animal were on the left side of the first graph where they already have lower glucose, but the mean should have been higher, while the animal in control group were from the other side, lower side, and this led to wrong rejection of null hypothesis. Means you thought that your drug worked, but actually it did not. You just took animal from two extreme, like extremely left and extremely right of the population size. So type 1 error is occurred. Now the question is how we can avoid type 1 error. So you can lower level of significance alpha to reduce the chance of type 1 error, but the bad news is there is a price for this improvement. Changing the significance level will have the opposite effect on the chance of type 2 error. Lowering alpha makes type 1 error less likely and type 2 error more likely. Raising alpha makes type 1 error more likely and type 2 error less likely. So now in second case, if two groups control and treated, uh, yellow is treated and blue is control, yellow is treated group and blue is control group, had significant difference in their mean sugar level, but the animal data that you chose was from the overlapping region. Means you picked treated animal which had glucose much higher than mean, and you picked control which were much lower than expected mean. So in that case, your drug actually worked, but you accepted the null hypothesis. This is where you commit type 2 error. So while it is impossible to completely avoid type 2 errors, it is possible to reduce the chance that they will occur by increasing your sample size. Means if sample size is large, so chances of occurring type 2 error is less. So now let's learn a hypothesis testing in GraphPad Brain with an example of enzyme kinetic data.